Hi there, this is David Williams. This is my first video in a series of Boolean algebra simplification videos. I'm just going to go through a number of different examples. In this video, I'm going to start really simple. But before I do any examples, I just want to refresh your memory with a summary of a few Boolean algebra properties and theorems. If you haven't seen these properties and theorems before, I suggest that you find a resource to read up about them. And just to familiarize yourself with the basic theorems, the basic properties, because we're going to be using them as we do the Boolean algebra simplification. If you'd like, take a screenshot of these properties and theorems so that you have it beside you as you watch this video. Remember that the basic idea and the reason behind Boolean algebra simplification is that you may have a circuit that's implemented with logic gates looking like this, but you want to make sure that you're using as few gates as possible. And so you want to simplify the Boolean algebra expression that you're trying to implement in logic so that you can use as few gates as possible. In this problem here, we'll note that we have an x ANDed with an x. So anytime that you have a literal ANDed with itself, it's just the literal. So x ANDed with x is simply x. So we have x then ANDed with z and then ORed with w, and that's as simple as we can get this one. In this example, we're going to use the fact that when you have an AND expression like this, L and M and N, it doesn't matter what order you do that ANDing in, it still gives you the same result. So I'm going to rearrange this to be M, L, N, and then that's ORed with ML. Now I can notice that I have an ML part of the term here and an ML part of the term here. So what that means is I can factor the ML out of both of those expressions. So if I factor ML out of the first expression, I'm left with N. If I factor ML out of the second expression, I'm left with 1. Now anytime that you OR something with a 1, you're simply left with 1. So this will be ML ANDed with 1. Anytime you AND something with 1, that's just going to be that something. So in this term, in this particular expression, ML ANDed with 1 will simply be ML. In this expression, I'm going to look at this part of the expression first and then look at this part of the expression. So over in this part of the expression, I'll notice that I have a D ANDed with a not D. Anytime that you have a variable ANDed with the inverse of itself, that's going to give you 0. So we will get here A or B ANDed with 0. And of course, anything ANDed with 0 is simply going to be 0. Over on this side, we have another variable and the inverse of itself, but this time we're ORing the two together. So anytime you OR a variable and its inverse, that's going to give you 1. So here we'll get 1 and D. Any variable ANDed with 1 will just be that variable. So we have now 0 ORed with D. Anytime you OR a variable with 0, it will simply be the variable. So in this case, S equals D. Looking at this expression, it might not be so obvious how you would simplify it. However, if you go back to the summary, the expression that we are trying to simplify follows the form of this expression right here. So it's actually just a one-step simplification. So taking this idea that A ORed with not A, B is equal to A or B, we can recognize the pattern in this expression. This expression is in a slightly different form, so if we wanted to rearrange just to be totally sure, we've got A, B, or not A, B ANDed with C. So the A, B in this expression is analogous to the A, and the C in this expression is analogous to the B. So then overall, this expression is simply going to be AB ORed with C. Here's a similar example, but I've got the inversions or the not operations on different parts of the expression. So what if we had W is equal to not U ORed with U and not V? In this expression, this is exactly the same as this expression up here, except obviously I'm using different variables, but the place that I have the inversion is in a different place. But the not U here is analogous to the A up here, the not v here is analogous to the b up here. So this simplifies to not u ORed with not v. Okay, I think I'll do one more example in this video just to make sure we keep it under 10 minutes, and then we'll step it up in the next Boolean algebra simplification video. So looking at this expression, not much I can do with this individual part, but on this part I could do an expansion. So we'll leave the AB there. So basically ANDing the B through the other components in this part of the expression. B ANDed with B, ORed with B ANDed with not C, and then finally ORed with not B and C. So B ANDed with B, that's simply B. So I'll rewrite the expression here. AB ORed with B, ORed with B and not C, ORed with not B and C. Now looking through the expression, I'm looking for common factors, the common B through three of these parts of the expression. So I can factor out B from each one of those terms. Take factor B out of this expression, I'm left with A. Factor B out of this part of the expression, I'm left with 1. Factor B out of here, I'm left with not C. And then I just have the not B and C here. Inside the brackets, I'm ORing with a 1. So that means this whole expression is going to be 1. B ANDed with 1, ORed with not B and C. Anything ORed with 1 is simply, anything ANDed with 1 is simply itself, or not B, C. Now that I'm down to this expression, I should recognize that this is very similar, or basically identical to the form of the previous two examples I looked at. A variable ORed with itself inverted, ANDed with another variable. And that, of course, is just going to be equal then to B ORed with C. There is one more thing that I want to do because I promised a little bit earlier in the video that I would prove that this expression here is true. To go about this proof, I want to write out a slightly different expression, A or C ANDed with A or B. Now let's figure out what this is. So all I'm going to do is multiply this out or expand this expression out and see what I get. So A ANDed with A gives me A. ORed with A ANDed with B gives me AB. ORed with C ANDed with A gives me AC. ORed with C ANDed with B, CB. Now in each one of these parts of the expression I have a common A factor, so I can factor that A out. So factor A out of the first term here, I'm left with A. Factor A out of the second term there, I'm left with B. Factor A out of the third term there, I'm left with C, or CB. Anytime that you're ORing expressions with 1, you're simply left with 1, so this will be A and 1. Any expression ANDed with 1 will simply be that expression. So basically that whole part of the term goes away and I'm left with just A or CB. Now let's let C equal not A. Now going back to this side of the equation, that will rearrange it or change it to be A ORed with not A ANDed with A or B. And the other side of the equation will become A or not A ANDed with B. Looking again at the left-hand side of the equation, A ORed with not A is simply going to be 1. So that whole term goes away and I will have simply A or B on the left-hand side of the equation is equal to A or not A, B, which is exactly what I was trying to prove. So I hope you learned something in these few Boolean algebra simplification examples, and I'll see you in the next one.